Hi Year 11, so this video is going to go through the questions that you completed while you were doing your virtual learning for atomic physics. So this video has both the triple questions and the coordinated science questions as well, and I'll add links to each individual question so that you know where to go depending on which booklet you worked on. So the first page was just your list of syllabus points, so you know what you need to be able to do, so that's always a good thing to refer back to. So part 1 was about the nuclear model of the atom. So in question 1, so which of the following is not a charged particle? This one's just a memory game, so you need to know that an alpha particle is a helium nucleus, which is 2 protons and 2 neutrons. We know that protons are positively charged, neutrons have 0 charge, so overall we have a 2+ charge on an alpha particle, so it can't be that. A beta particle is an electron, which is negatively charged. A proton is obviously a +1, and a neutron is a 0 charge, so that should have been pretty straightforward for you. In question 2, which statement about the nuclei of all atoms is correct? There were a surprising number of you that got this question wrong. A lot of you chose B. They always contain the same number of protons as neutrons. That's not true. If you look at your periodic table and we take even lithium, for example, which is 7 and 3, that means we have 3 protons and 7 minus 3, which is 4 neutrons. We don't always have a balance of protons and neutrons. So please make sure that you get rid of that misconception. What you do need to remember is that the nucleus is very, very small in comparison to the size of the whole atom, because we have to take into consideration the electrons in orbit, and most of the atom is actually empty space. The nucleus does not take up much space at all, so just make sure you've corrected that if you got that wrong. 3, a certain element is known to exist as 2 different isotopes. State one thing that is the same for atoms of both isotopes. So that's the proton number. Some of you wrote atomic number, which is okay. State one thing that is different between the atoms of the 2 isotopes. It's the neutron number. So again, we're starting off with just memory. In question 4, though, it got a little bit trickier. So in Geiger and Marsden's alpha particle scattering experiment, alpha particles were directed at a very thin gold foil. Figure 10.1 shows 5 of the nuclei, so we've got 5 gold nuclei in one layer. Also shown are paths of 3 alpha particles directed at the foil. Complete the paths. So this is an alpha particle coming in, and you can hopefully see that it's coming in very close to the nucleus. Now we know that an alpha particle is positive, and we also know that the gold nucleus is positive because it's filled with protons and neutrons, but the protons give it its positive charge. We know that positive charges repel each other, and so because this comes close enough, there will be a repulsive force. That force changes the path slightly, so we want to see some deflection. The second alpha particle actually doesn't come into contact with any. It can go straight through the empty space. It's not coming close enough to feel that repulsion force, and so your second one just needs to go straight through undeflected. Your final one, your final alpha particle coming in, you can hopefully see will hit the alpha particle, the gold nucleus, head on. Imagine running into a wall. Okay, it will make you bounce back. This gold nucleus is much heavier than an alpha particle. Okay, gold has a very large atomic number compared to alpha, so this thing's just going to bounce straight back. So those were the paths that you needed to draw. So it then said in part B, what result of the experiment confirmed that an atom consisted of a very tiny charged core containing almost all the mass? So what we're saying is, which one of these provides proof that there must be a lot of mass in a very small space? Well, it's going to be the one that causes it to bounce back. If this were not very massive, if this were very, very light, we wouldn't necessarily get a bounce back. We might just get a bit of a collision and it will carry on. But because this is so heavy, we know that the mass is concentrated here. Because we get the bouncing back, it confirms to us that we are seeing that. So that's the one that you should have chosen there. Okay, so then it asks, what is the sign of the charge on this core? So we know that an alpha particle is a helium nucleus, so it's positive. So it therefore makes sense that because we have repulsion, that they must have the same charge. So therefore it tells us that we must have something that is positive. And then the last question, part of this question, is that it asks what occupies the space between these charged cores. So we know that given that most of the alpha particles went straight through, they cannot have interacted with anything. So therefore it must be empty space. It must be a vacuum. So part 1, question 5. Again, this caused quite a lot of problem. So an atom of one of the isotopes, so we know that we've got isotopes of sodium, which means that we always have sodium, so we always have the same number of protons and electrons, but because they are isotopes, they may have different numbers of neutrons. So it says, underline which of these 3 will be the same in neutral atoms of all isotopes of sodium. Now, I want to give you some exam technique advice. If it's out of 2 marks, you are not going to get 2 marks from one line. So that should give you a clue that you need to refer to more. So if they are neutral atoms of isotopes of sodium, what we know is that every positive must have a negative to cancel out. And so therefore we must have equal numbers of protons and electrons to make sure that we have a neutral atom. Okay, because if we have more protons than electrons, it would be positive, and if we had more electrons, we'd have something that's negative. So you need to underline the protons and the electrons. In part B, it says, state the nucleon number of this isotope. Nucleon number is not neutron number. Neutron is obviously how many neutrons you've got. Nucleon is how many things do you have in the nucleus. So that's the protons and the neutrons. So we have 11 protons and 13 neutrons, and when we add those together, we get 24. Now, part C is actually really a chemistry question, so this was a bit mean. So it was me saying, if you're thinking about it from your chemistry lesson perspective, what can you say about the chemical properties? So things like boiling point, melting point, solubility, that kind of thing. About the different isotopes of sodium. Well, it's still sodium, it's still the same element, and so chemically it will react the same way. It's only once we've got a different element that we can say the chemical properties are different. So that's just one to be aware of. In part D, you're given an isotope of sodium, but this time with a nucleon number of 25. How many neutrons are there in one atom of this isotope? So we know that sodium must have 11 protons because the atomic number for sodium is always 11. Okay, so therefore, if the total number of neutrons is 25 and 11 of those were protons, the difference will be the number of neutrons, so that gives us 14. In question 6, this is part 1, question 6, the diagram shows alpha particles incident on a thin metal foil. How does the motion of these particles give evidence for the nuclear atom? So what this is saying is, how does what happens to the alpha particles tell us that our atom looks like a nucleus with electrons orbiting? How does that help us see that? Most particles passing through with minimal deflection shows that the atom is mostly empty space. Makes perfect sense, because what we're saying is, if we're an alpha particle here, we're not going to interact with the nucleus. If we're an alpha particle here, we're not going to interact with the nucleus. If we're here, you get the idea. Most of them are going to be able to get through without interacting with the nucleus, and so we must have mostly empty space. Okay, so that gives us answer A. In question 7, a very important experiment, same experiment, improved scientists' understanding of the structure of matter. The experiment involved alpha particles being fired at a thin gold foil. What happened? You need to remember this. It can't be that the alpha particles were absorbed. They weren't absorbed. We found them around the experiment. We found them either on the other side, we found them deflected back, we found them deflected up, but they never disappeared. Okay, so that's not true. Not all of them were unaffected. Some were unaffected. However, we did see some get deflected. In C, some alpha particles were attracted by the neutrons. Absolutely not. Neutrons are neutrally charged. There will not be any force of attraction or repulsion between something that's neutral. And then D, some of the alpha particles were repelled by the protons. So that makes perfect sense. So it's D. In part 2, again, this relies on your chemistry. And again, there were quite a few mistakes. So let's just go through these carefully. So part 2.1, a nuclide has the symbol 2311. Which statement about all of the atoms of this nuclide is correct? Well, we know that the bottom number is always protons. The top number is protons plus neutrons. So therefore, we must have 11 protons because our Z number is 11. Okay, so that's just one that you have to remember. In 2, the symbol represents a nucleus of zinc, which row gives the number of protons and the number of neutrons. So we can easily write off C and D because the bottom number is the proton number. The top number is the mass number, it's protons plus neutrons. So what we have to do is take that big number minus the number underneath it, and that must be how many neutrons we are left with. So that gets us to 38, which gets us to A. 3, again, this question a lot of people got wrong. So 4 nuclides are represented below. Which pair are isotopes of the same element? So we know that if we have a particular element, we must have a very fixed number of protons. And that is the atomic number. That's the bottom number that we're looking for. So we need to look for 2 that have the same bottom number for it to be the proton number, which gets you A. Okay. In question 4, a simple model of the atom consists of small particles orbiting a central nucleus. Which row is correct? Let me zoom in just a little bit so we've got it a bit clearer. So the nucleus, we know, contains protons and neutrons. Okay, we know that they are positive. Orbiting particles are the electrons, which we know are negative. So that is just one that you need to remember. In question 5, an atom consists of a nucleus made up of protons and neutrons surrounded by orbiting electrons. Which of these particles has a positive charge? Protons are positive. Which 2 of these particles have almost equal mass? This lots of you got wrong. So remember, in your nucleus, you have protons and you have neutrons. They're relatively the same size. Okay, so the P and the N are approximately, not completely identical, but pretty much the same size. And around the outside we have these tiny electrons in orbit. They're much smaller. So we should be saying protons and neutrons here. A silver nucleus is denoted by Ag with 147. State the number of protons and the number of neutrons. It's the same type of question. The bottom number always tells us the number of protons. The top number tells us protons plus neutrons, so we need to take the proton number away to get the neutron number. So we're looking for 60 there. Okay, question 6. Again, there were quite a few mistakes. So we have a neutral lithium atom. All the particles in the atom are shown on the diagram. How many electrons do we have? Most people got this right. We can count 1, 2, 3. Now, because it is neutral, for every negative we have to have a positive. So it must be that the proton number is also 3. We can see then that that must be the ones I've coloured in purple. I think yours were white. Okay, which leaves us remaining 1, 2, 3, 4 left over to be the neutrons. Okay, and then the nucleon number is the protons plus the neutrons. So we add the 3 and the 4 and we get 7. And then you're just showing that you know that the top number is protons plus neutrons and the bottom number is protons only. Part 3, question 1. So this is about ionizing radiation. So in some areas there are high levels of background radiation. Explain what is meant by background radiation. So many of you got 1 mark out of 2. You often said it's radiation that's always in the environment. That makes sense. But remember that light is also radiation, and we're not worried about that. What we're looking at is radioactive particles or gamma rays being emitted that are ionizing. So this word here needs to be in your answer. It's the ionizing radiation that we're counting as background radiation. Okay, and it's a Geiger counter that we use. Many of you got this right, so well done, to detect background radiation. Complete the table for the radon gas, which is radioactive, to show the number of each type of particle in a neutral atom, which helps us because if we're neutral, we have the same number of protons and electrons. The bottom number, 86, is protons, therefore is also electrons. The top number, we know, is protons plus neutrons, is equal to 219. 86 of those were protons though, so the remaining ones, 133, will be the number of neutrons. That was a problem for a lot of people actually, so just make sure that you are feeling confident with how to find neutron number. In 2, a radiation detector measures a background count rate in a laboratory of 32 counts per minute. Suggest 2 naturally occurring sources of background radiation. So, there were 3 categories that you had to refer to. You couldn't have 2 from the same category because they essentially are the same thing. So, if you said rocks or buildings or the ground or the earth or stones, we're talking about the physical building blocks that we find on Earth. So that's 1. Space, if you said the sun, the stars, galaxies, cosmic rays, that counts as a 2nd. And then finally, radon gas in the air on Earth is also a 3rd mark point there. Okay, so you have to have them from separate categories, otherwise you're talking about the same thing. So, question 3. A teacher holds a radioactive source near a detector. The reading on the detector is 320 counts per minute. The detector is switched on again after the source has been removed. Okay, so this means that if we've removed the source, the detector must only be showing the background radiation, and it shows a reading of 20 counts per minute. What is the counts per minute solely due to the source, and why is there a reading on the detector when there is no source present? So, we know that when we have the source nearby, we see 320. So that must mean that the Geiger counter is detecting 320 in total from both the source itself and also the background. We know that the background was 20, so if we take that off the number, we must have what the source was providing. Okay, so that gets us 300. And the reason we see a reading, even when we remove the radioactive source, is that there is still background radiation. So that gets us to B. Okay. Question 1 was not a marking point. You can pause the video so that you have got corrections if you need them, but they were just for your memory and to be able to answer the rest of the questions. So in question 2, of the 3 types of ionising radiation, alpha, beta and gamma, why does alpha emission cause the most ionisation? Okay, so alpha is 2 protons and 2 neutrons. Beta is an electron. Gamma is part of the electromagnetic spectrum. It's a wave. And so this doesn't have any mass. An electron is very, very small. Alpha particles are quite big because they've got 2 protons and 2 neutrons, so they're very massive. Okay, this makes sense because what's happening is, let's say I send alpha, beta and gamma into the air, and the air has lots of molecules. If this alpha particle is travelling through, it's very likely to hit one of these molecules, and when it hits it, it collides and it knocks electrons off orbit, and that's ionisation. That's more likely when this is bigger compared to these two, because this thing's so small it's more likely to just whiz straight through. Okay, so what we're looking for is alpha particles have the greatest mass. In question 3, radium is an alpha emitter. It's implanted inside cancerous tumours. It is safe to use it as it kills the cancerous cells, but not the healthy ones surrounding the tumour. Which properties of alpha compared to other emissions enable this use of radium? So, we know that alpha particles have very high ionising ability because they are very likely to collide with the things that they travel through, and therefore they're likely to knock electrons off orbit and therefore ionise things. What that means though is that if you collide with things lots of times, they're going to lose energy themselves. The alpha particles, when they hit other things, they transfer that energy away, and as they lose energy they slow down and they get to a point where they stop. And that happens very quickly because they are colliding with lots of things. So they don't get very far, and penetration is saying how far can they go. So therefore we have low penetration if we have high ionisation abilities. Okay, question 4. A thin sheet of paper is placed between a radioactive source and a radiation detector. The count rate falls to a very low reading. From this result, which type of radiation is the source emitting? Well, we know that only alpha particles are stopped by paper. So therefore, if the paper did cause it to fall, it must be that it was stopping alpha particles. So that just gets you A. In question 5, which statement about gamma radiation is correct? Again, you just have to remember it. It is a form of EM radiation. Okay? It's not a particle. It's highly penetrating, but it's the least ionising of all 3. In question 6, A student measures the level of radiation emitted from a radioactive substance. He places a detector very close to the substance and he puts different absorbers between the radioactive substance and the detector. The results are shown. These are the results. So we can already see that we've got things being put in the way of the detector. Nothing, so everything would get through. A thin piece of paper, which we know would stop alpha. A few millimetres of aluminium, which we know will stop beta, and several centimetres of lead, we know that would stop gamma. So we know what these things should do. So then we see what happens to the numbers, and it will tell us what we must have had. So when we introduced paper, you will see we had a very big reduction in reading. So it must be that the paper managed to stop something. The only thing that can be stopped is is alpha. So therefore, we know we're looking for one with alpha in. So we can get rid of C because it isn't an option. When we go from paper to aluminium, we don't see any change. Okay, whereas we know that if there were beta, it would get through the paper, but it would be blocked by aluminium. So if we had beta, we would expect to see a drop when we got to here. Because we don't, we cannot have beta particles. And that means we can remove these ones, leaving us with B. And we can check it because we can see when we introduce lead, we see a drop, which makes sense because it blocks some of the gamma. Excuse me. So there you go. So that's number 6. That's a bit of a tricky one, but you can see that we're getting lots of similar type of questions where we're having to be aware of what gets stopped by which type of absorber, and knowing that allows us to answer the questions, so you must memorise them. Question 7 then. A sample containing atoms of the radioactive isotope polonium-208 is removed from a lead container and brought close to the detector. The average count rate increases to 890 counts per minute. When 2 sheets of paper are inserted, the average count rate returns to 40 counts per minute. So we know that the reading has been massively reduced. Paper can only block alpha, so it must be that it was alpha that was being emitted in the first place. So that gets you 1 mark, and the second mark comes from saying that's because alpha does not penetrate paper, and we saw the count rate reduced, so it must be alpha. Okay, question 8 then. This was a tricky one. Figure 11.1 shows equipment that is used to investigate the effect of a magnetic field on the path of a beam of gamma rays. The information at the top of GCSE questions is important. Don't ignore it. Okay, a radioactive source emits gamma rays. Now we know that gamma rays will be being emitted in all directions. Okay, the source doesn't miraculously know where to direct the gamma rays, so what we actually have are many gamma rays in all directions, but what we wanted was a beam. Okay, so it says suggest the purpose of the 2 lead plates. Now we know that lead absorbs gamma, so what it means is if there's a gamma ray going this way, it won't track through and it won't enter this area because it will get absorbed, so it will only allow the ones through the gap, which makes sense because that then allows us to have a very thin beam. So the purpose of the 2 lead plates is to produce the beam. Okay, so rather than just lots of gamma in all directions, we now have only one direction that they're travelling in, towards the detector. So that's your 1 mark there. Then in B, this was tricky. State the relative ionising effects of alpha, beta and gamma and suggest an explanation for the differences. So relative ionising effects mean make a comparison. How are they compared to each other? So what you needed to say for 1 mark was that the alpha ionising effect is greater than the beta ionising effect, which in turn is greater than the gamma ionising effect. You can do it in bullet points. You can write it exactly like this. You can put it in words, so long as you've made it very clear that you understand that alpha is the most ionising and gamma is the least. Okay, and then your explanations for why this is the case is because, well, we've talked about this, the mass of the alpha particle is much bigger than the mass of the beta particle. So it's more likely to collide with things and knock electrons off their shells and ionise things. Okay, whereas gamma, because it's massless, is very unlikely to do that. The second mark point for your explanation is because the speed of the alpha particle is much smaller than the speed of the beta particle. which is much smaller than the speed of the gamma particle. Okay, you could also have talked about charge, but you want 3 distinct mark points. I've done those in colours so you can see them. The crucial one was your purple one though, you needed to get that first. Part 5 then, sorry, move my things around. We've got a radioactive nucleus of carbon decays to a nucleus of nitrogen by emitting a particle. Complete the equation and state the name. So, we know that we can't just magically create particles out of nowhere and they cannot disappear. So, in total, my total nucleon number before has to equal my total after, and same for my atomic number, has to be the same before and after. So if I have 14 on the top, 14 here, this must be a 0 to conserve nucleon number. And if I had 6 before, but a 7, I must have a -1 because 7 minus 1 equals 6. Then I know that I've got something that has nothing inside of the nucleus because the nucleus is 0, but it has a charge of -1, so it must be an electron, it's a beta particle. So you've got 1 mark for each number and 1 mark for the particle. 2. Technetium-99 is a source of gamma rays often used as a tracer. So it gives you some nice helpful information that's not necessarily so helpful. It is produced from molybdenum, doesn't matter, which emits beta particles. The symbol for technetium is Tc and the symbol for molybdenum is Mo. Complete the nuclide equation for this decay. Even if you didn't read any of that top bit and you just saw this bit, you should still be able to do it because we know that nucleon number is conserved. So 99 before means we must have 99 and 0. Because we know that a beta particle is an electron, we know this is 0. Okay, there's nothing inside a nucleus in terms of electrons, so that's a 0. Okay, because we also know this is a beta particle, we know it's an electron, this is a -1, which tells us that this must be 43 because 43 minus 1 is 42. Okay, this next question wasn't done necessarily too well. So there are 3 naturally occurring isotopes of hydrogen. Again, it's an isotope, so the proton number is the same for all of them. This is hydrogen 1, so we know then that it's 1 proton. Okay, a singular proton is hydrogen 1. Hydrogen 2 tells us that we have 2 nucleons. Only one of those can be a proton because it's hydrogen still. Okay, so we still have 1 on the bottom, but our nucleon number is 2. And then same for hydrogen 3. Okay, it's still hydrogen, so it still has 1 proton, but it's got 3 nucleons in total. So hydrogen 2 would be 1 proton and 1 neutron, and hydrogen 3 would be 1 proton and 2 neutrons. Okay. In a fusion reactor, a nucleus of hydrogen 2 and a nucleus of hydrogen 3 undergo fusion. State what is meant by nuclear fusion. So this is where you need to say 2 smaller. Now this is important, nuclei, because it's asking about nuclear fusion rather than atomic fusion. 2 smaller nuclei joined together to make a larger nuclei, 1 mark, releasing energy, which is the 2nd mark, because the whole process releases energy. Okay, so 1 mark before the comma, 1 mark after. Part II. The fusion reaction produces a free neutron and 1 other particle. Write down using nuclide notation the equation that represents this reaction. So, the fusion reaction, we were told, is between H2 and H3. So, I take my notation from the top and I'm combining these two in fusion. I know that that leads to a reaction that produces a free neutron. So my neutron is a lowercase n. If you do capital N, that's the element symbol for nitrogen, so it doesn't make sense, so don't do that. Lowercase n. No protons, but 1 neutron. Okay, so therefore, on the top, before I have 5, if I get 1 from the neutron, I must have 4 here, because 4 plus 1 is equal to 2 plus 3. 1 plus 1 before equals 0 plus 2. So I know I have a 4, 2, and I know that that is an alpha particle, because that's just something you need to remember, that an alpha particle is a helium nucleus. Okay, so we just use our numbers to help guide us. In part C, nuclear fusion in the Sun is the source of most, but not all of the resources that are used to generate electrical energy on Earth. State 2 resources for which nuclear fusion in the Sun is not the source. So what we're saying is, which resources do we have to generate electrical energy do not rely on the Sun? So this is going back to year 10. We remember, hopefully, that geothermal is heat stored underground. That's got nothing to do with the Sun. Nuclear fission is where we've got uranium being bombarded with neutrons and splitting up. Nothing to do with the Sun. And tidal energy is to do with the Moon and its gravitational pull. So these three were options that you could have chosen from. Okay, question 4 then. Uranium-235 is a radioactive isotope of uranium that occurs naturally on Earth. Okay, this did catch a lot of you out. Describe the composition, so that means what it is made of, and the structure, what it looks like, of a neutral atom. So, what it is made of? Well, it contains 92 protons, we're told that here, plus 235 minus 92, which is 143 neutrons. Okay, so remember this 235 minus the 92 is the neutron number. And that was the 143. So it's gone off the page. Okay. It's also helpful because it tells us it's neutral. Therefore, we must have the same number of protons and electrons. Sorry, I've written 93, but this should say 92. Okay. So that's my composition. It tells me what I have. Okay, and then the structure, what it looks like, is the atom contains a nucleus surrounded by electrons. So you could have said the atom contains protons and neutrons in the nucleus surrounded by electrons, but you would also have gotten marked for the way that I have said it as well. Okay, so each of those were worth 1 mark there. In part B, it says another isotope of uranium is uranium-238. It's still uranium, so the proton number has to be the same. But we've gone from 235 to 238. So that's a difference of +3. So therefore, it has the same number of protons, but a different number of neutrons. Or you could say U238 has 3 more neutrons. That would also be fine. Okay. In part C, it was just about completing and balancing the equation. Now, what you need to be aware of is that we have a fission reaction where we have a slow-moving neutron. So remember, a neutron is a 0, 1, because there's no protons, but we do have a nucleon number. This is important. The 2n means we have 2 lots of neutrons. So therefore, 2 times 0 is 0, but 2 times 1 is 2. Okay, so what we have on the top before is 236, and what we have on the bottom is 92. That has to be the same on each side. So 140 plus 94 plus 2 is 236. Okay, on this side, 54 plus 38 plus 0 is 92. So that's how I know these two numbers that are missing. Okay, because I have 2 neutrons that I have to account for, but everything on the top on the right hand side has to equal everything on the top on the left hand side. So that's quite a tricky one. In part D, it says xenon is radioactive. It decays by beta emission to isotope Q. Determine the proton number of Q. So if it decays by beta emission, an electron has been emitted. That's what beta is. So therefore, if an electron has been emitted, the atom has got less negative, which means it has got more positive. It has gained a proton. Okay, so therefore we must have a number that is larger than it was before by 1. Okay, so if we've lost an electron, we've become less negative, which means we've become more positive. So we're now plus 1. So 54 goes to 55. It's an isotope, so it is the same in terms of, sorry, ignore me. That was a terrible explanation. I'll try again. So let's try it with an equation. Actually, I think that might help you more. So we've got xenon, which is 14054 Xe. It decays by beta emission. So let's add a beta particle, which is -1 and 0. So therefore, I must get an isotope Q where this is 55, such that 55 minus 1 is 54, and this must be 140 in order to conserve our numbers. That's probably a better way of doing it, actually, is writing out your equation. So sorry, it's not very clear, but hopefully that is okay for you. Come find me if it's not. In question 5, a radioactive nucleus contains 138 neutrons. The nucleus emits an alpha particle. Remember, that's 2 protons and 2 neutrons. How many neutrons are in the nucleus after the alpha particle has been emitted? Well, we've only lost 2 neutrons, so all we have to do is take our original number and minus 2, and that gets us 136. So in question 6, we've got uranium-235 is a radioactive isotope. It undergoes a chain of decays and eventually forms the stable isotope lead-207. So there's lots of things happening between here and here, but this is our starting value and this is our final value, and between that, particles must have been emitted. During this chain of decay, how many protons and how many neutrons are lost from the atom of uranium to form this? So we go on the top from 235 to 207. So we must have lost 28 nucleons. To go from here to here, the number of nucleons is 28 less. We've gone from 92 to 82 on the bottom. So we must have lost 10 protons because the bottom number is the number of protons. So we look for 10 protons, that gets us A or B. But we know that in total, protons plus neutrons lost was 28. 10 of those were the protons, therefore 18 of those were the neutrons, which gets us answer A. Okay, question 7 then. Uranium-235 can undergo nuclear fission in many ways. Which equation correctly shows a possible fission reaction? So all we have to do is check that the numbers on the left are equal to the numbers on the right. So on the top we've got 236. On the bottom we've got 92. On the right hand side on the top we've got 141 plus 92 plus 3 is 236. It's correct. 56 plus 36 plus 0 is 92. So the numbers all add up. Don't forget that this big 3 scales all of these numbers by 3. We've got 3 lots of 10 neutrons. Okay, so that's why I've got 3 here. So that gets me answer A. In question 8, the chemical symbol for sodium is Na. We've got an equation representing the decay. What are the numbers x and y? So everything on the left equals everything on the right. 24 must equal 24 plus y, therefore y is 0. 11 must equal x plus minus 1, so therefore x must be 12. And then you just choose the right one. Number 9, we've got a radium nucleus, decays by emitting an alpha particle. Don't forget that that's a 4-2 helium nucleus. The proton number of radium to begin with is 88. What are the nucleon number and proton number for the nucleus produced by this decay? So let's write the equation out. We start with our radium, 226, 88. We are told it emits via alpha plus whatever we're left with. Okay, so 222 plus 4 is 226. 86 plus 2 is 88. And that tells me my numbers that I'm looking for. In question 10, the nucleus of an isotope of nitrogen absorbs a neutron. It then decays into an isotope of carbon and emits X. So again, let's add the numbers to help us out. So we've got 1 plus 14 must equal 14 plus 1. 0 plus 7 must equal 6 plus 1. So I know that I've got a 1, 1 here. I've got 1 as my atomic number, so I've got a proton. And I've only got 1 nucleon number, so I must just have a proton, which is also a hydrogen atom. Part 6 is where it got a bit tricky for you all. So, a sample of radioactive isotope in question 1 is placed near to the detector and a count rate of 112 counts per minute is recorded. After 18 hours, the count rate is recorded at 28 counts per minute. Determine the half-life of this isotope. So, after each half-life, the count reading will halve. So if we started with 112, after one half-life, we divide that by 2, we must have 56 remaining. After another half-life, this value halves, so we're left with 28. Okay, so I've halved it twice. I can see that I got to 28 after 2 half-lives, okay? And therefore, this reading occurred at 2 half-lives. So it took 18 hours for 2 half-lives, therefore 1 half-life must be 9 hours. Okay, so don't forget, we just take our original number, halve it, that's 1 half-life. Take this number, halve it, that's our second half-life, and we keep going. Okay, question 2, explain what is meant by the term half-life. It's the time taken for the number of radioactive nuclei in a sample to halve. Okay, question 3 is probably one of the hardest questions in the entire booklet. So let's see if I can get us all seeing all of it. Radon 222 has a half-life of 3.8 days. At a certain time, a sample contains 6.4 times 10 to the 6 radon nuclei. Calculate the number of alpha particles emitted by the radon nuclei in the following 7.6 days. Okay, if the half-life is 3.8 days and we are looking for a total of 7.6 days, we must have had 2 half-lives occurring, because 7.6 divided by 3.8 is 2. So, in 2 half-lives, my original number will have halved twice. So after 1, my 6.4 goes to 3.2. After 2, the 3.2 halves to 1.6. Don't forget about the times 10 to the 6. This tells me that after 7.6 days, I have this many nuclei left to decay. Okay? It asks you to calculate the number of alpha particles emitted. Well, you only get emission of alpha if a decay has happened. This is how many I had to begin with undecayed. This is how many I had at 7.6 days. So I must have had the difference between those two is how many actually decayed in that time. Okay, so 6.4 times 10 to the 6 original undecayed minus the 1.6 times 10 to the 6 left undecayed at the point we're interested in must equal how many decayed in that time. So my value that I have to quote is my 4.8 times 10 to the 6. Okay, not the 1.6 value, because that's how many were undecayed, and what we need is the number that were decayed. In question 4, we've got a count rate graph, but this time we have to consider that there is background radiation. So, in a power station, a detector is connected to a computer. The detector is switched on. So this is before anything happens, we switch the detector on, and you can see for the first 10 minutes that we have a reading of 12. Okay, everyone got that? Use figure 11.1 to determine the background rate. So, in the background, we had 12 counts per minute. At the 10-minute mark, we place the source near the detector and we suddenly see a huge spike in count rate. We read it to be 84 at t is 10 minutes. But remember that 12 of those 84 came from the background. But it's not asking for that, it's asking for the ones from the radioactive sample. So we have to take the 12 away and we get 72 counts per minute. We do the same at 19 minutes. Again, you need to be very careful with your read off. Lots of you chose 20. You have to read to the nearest half of a square. It's actually 21. So at 19 minutes we had 21, but 12 of those were due to the background. So the answer is actually 9. So that bit caught a lot of people out. In C, it says use the values obtained in B, so use these numbers, to estimate the half-life. Okay, well, if we started with 72, we know that after one half-life, it would decay to half, 36. After two half-lives, this would half again to 18. After three half-lives, it would decay again to 9, which is actually what we found. So we know that between this time where we had 72 at 10 minutes and this time where we had 9 at 19, we moved through 3 half-lives. That was between 10 and 19 minutes, so it took 9 minutes, that's the difference between the two, for the 3 half-lives. So if 3 half-lives is 9 minutes, then 1 half-life will be 3 minutes. And that's how we get our answer for C. But again, this was something that people found very difficult. Come and find me if you are still stuck. Okay, the half-life for lead in question 5 is 52,500 years. A sample of lead produces 800 counts per second. How long will it take to drop to 100 counts per second? So again, you just have to write it out. If we start with 800, after one half-life, that halves to 400. After the next half-life, that halves to 200. And after the next half-life, that decays to 100. I know then that I took 3 half-lives to get to the number that I'm looking for. So I've got 3 lots of how long it takes in one half-life, and when I get that, I get answer B. Question 6. The graph shows the decay curves of 4 different radioactive isotopes. Which has the largest half-life? Largest half-life means it takes the longest for the thing to decay, for the radioactive source to decay. So it means it's going to be the slowest decay we see. So what that means is we're not going to see any change in count rate because there's nothing really happening. Okay, so therefore we're looking for the one that doesn't really change, so we choose A. Sorry, I'm getting a lot of emails clearly. Question 7. Oxygen 15 is used in hospitals. The count rate from a detector placed close to a sample of oxygen was recorded over a period of 15 minutes. Again, sometimes they include background, sometimes they don't. If they do, you have to factor it into your calculation. The background count rate is 20 counts per minute. What is the half-life of the sample of oxygen? So initially, we read a count rate of 180, but we know that 20 of those came from the background. The background doesn't decay, so we know that all of our numbers are going to be off by 20. We must only have originally had 160 counts from the source. After one half-life, the source will decay by half, so the 160 turns to 80. But the detector will still be feeling the 20 background, so we have to add that back on to know that when we have 80 from the source, we'll actually get 100 on the counter. So what you're looking for is where we have the 100 to find our half-life. Okay, that's an important one to be able to do. In question 8, in part 6, the graph shows the activity of a radioactive source over a period of time. What is the half-life? No reference to background radiation here, therefore we assume there is none. So after one half-life, the original value of 120 halves to 60, which is at 2 minutes. Question 9, the count rate is measured for 80 minutes. At time is 0, so this is the initial number, we had 480. We take that number to help us work out what we will get after each half-life. After one half-life, 480 halves to 240. That happens to be one of the values we see occur later, so we can use this time because we know it must be the half-life. So that gets us C of 60 minutes. Question 10. A sample of a radioactive isotope emits particles at a rate of 240 per minute. After 48 hours, the emission has decreased to 15 per minute. So again, we just follow the same pattern. 240 after one half-life halves to 120. After the next half-life, this halves to 60. 60 will halve after a next half-life to 30. 30 halves to 15. We know that that took 4 half-lives to get to 15 per minute. So we know that 4 half-lives took 48 hours because it took us to 15 in 48 hours. So therefore, if 4 half-lives is 48 hours, 1 half-life will be a quarter of that. 48 over 4 is 12. Gets us C. Research task, I've checked in your books, doesn't count your marks here. Last but not least then, part 7, safety precautions. The diagram shows the paths of 3 different types of radiation, X, Y and Z. You can see plastic, aluminium and lead. We know that plastic stops alpha, we know that aluminium stops beta, and we know that lead stops gamma. We must memorise those facts. Therefore, the thing that stopped the plastic, the thing that the plastic stopped rather, was Y. So therefore Y must be alpha. The aluminium managed to stop X, so therefore X is beta, and the lead stopped the gamma, because that's what lead stops, so therefore Z is gamma, and you choose B. 2. Why are some radioactive sources stored in boxes made from lead? Lead will absorb all 3, and that prevents them from escaping out into the atmosphere where they can then interact with us, which would be dangerous. Question 3. State and explain one practical application of gamma rays. So the most obvious one is sterilisation of medical equipment. We know that gamma can penetrate the medical equipment. It's not going to get stuck in there. It's going to get all the way through. And therefore it's going to be able to interact with all of the bacteria and kill all of the bacteria for our explanation. Okay. In question 4, iodine also emits gamma radiation. It has a half-life of 8 hours. Explain why this emission in this half-life make it a suitable material. So why is it good at being a tracer in medical diagnosis? So we are using gamma to be able to look at things inside of the body. Well, firstly, gamma is the only one that can actually leave the body. So it's the only one that we will actually be able to detect in the hospital. If we use alpha or beta, not only is it likely to cause some very dangerous results, it's never going to leave the body, and we can't actually look at what we've seen being emitted. So that's not helpful. So that's part 1. Part 2 is that the half-life is only 8 hours. So although it is a radioactive source inside of a body, which is dangerous, it's short enough that it's going to decay really quickly, and it's not going to be dangerous for the human, and it's worth the 8 hours of radioactivity to be able to look at whatever the medical diagnosis is. Last but not least, in question 5, the substance emits alpha particles and gamma rays. A student suggests that it is safe to store the substance in a plastic container of thickness 2 millimeters. State and explain whether the student's suggestion is correct. Well, 1 mark just comes from saying no, they are wrong. Okay, and then the explanation, you could have had 2 marks from the following. Plastic will not absorb gamma. Lead is required to absorb gamma, so we need lead. Or you could have said the alpha will be absorbed by the plastic only, but the gamma won't be. Okay, so those were your safety precaution questions. If you've got any questions about any of the things that you've done in your booklet and you still don't understand following this video, you have to come and speak to me, because it's really important that you do understand.